allow me to arrive in place. I will continue this eROSITA-centric session, giving you an overview on all the work that has been done in order to allow you to harvest the AGN that are in the eROSITA survey that Andrea just presented. But I'm doing it also with an eye to future and current X-ray surveys, wide X-ray surveys, but you will see that is also what I'm presenting is also applicable to other wide surveys at other wavelengths. Are you okay with the recording? Let me start with a usual plot we always see when we speak on about X-ray surveys. You always have area versus flux. This is an old picture. You have redshift and luminosity. The color code for the surveys are depending on whether they've been observed with XMM or Chandra or eROSITA or ROSAT. And the point that I would like to make is that we spend 1 minute to realize that in the last 25 minutes, in the last 25 years, what we have learned in terms of galaxy AGN coevolution, how the properties of the AGN influence the galaxy, or the property of the galaxy as a function of the AGN property and so on, are actually coming all from pencil beam surveys. This means that these are small areas, relatively deep data, where the objects with the dominant AGN are actually rare. So we made the choice of making all our fitting, all our assumption, accepting that a few objects will not be good in our analysis because statistically there were very few. And we went on with our work and generalizing then later what we have learned from this specific type of low luminosity AGN to all AGN in general. And what I'm arguing is that with eROSITA, we are actually here for the first time opening a new parameter space. And we are always, when we are going to combine this data with the pencil beam data, we are really going to understand the role of the interconnection between the galaxy and the AGN. And here you can see in terms of luminosity and redshift, which kind of population eROSITA is opening up. But of course, because eROSITA is dominated by these AGN-dominated objects, an amount of work has been spent in order to be able to harvest then the data for making science. And so what I'm going to do is, starting from the catalog of Andrea, giving you the steps that brought up to the final catalog that of AGN that we are going to release to you. And at the end, I will have some remarks. So starting with identification, I'm sorry for some of you it's going to be boring because you know it pretty well. You have the X-ray sources on the left. You have on the right side the right counterpart. It can be a nearby galaxy. It can also be a star in a nearby galaxy, an ULX. It can be an obscured AGN. It can be an high redshift quasar. It can also be an unresolved cluster, or it can be a star in our galaxy. It can be any of that. And the goal is to find out among the many sources around the X-ray one, which is the right one. So in this case, this will be the guy, and this will be the right guy. And the problem is that you cannot do Ryan Deck in match, but you have to take into account the positional accuracy of the X-ray surveys. This is the work that we have done 2 days ago, presented 2 days ago in the eROSITA sources for XMM and Chandra in the Euclid data. You can see how the positional error of eROSITA force you to search for the counterpart much farther from the core of the position. So what I wanted to highlight here is that the accuracy of the counterpart identification depends on the area search, the ancillary data that you have, and the assumption that you are going to do on the type of X-ray emitter that you are interested on. In this slide, you have the X-ray sources in zenithal equal area projection. You have the south accretive pole, our deepest data. The color coded is in number density of objects. And below you have the maps of data that we are using for defining our counterparts. We are lucky that by the time eROSITA came out. It was late, and we were happy for that because meantime, all sky surveys came out online. So we are able to have the legacy survey, DR10, that cover essentially the entire extragalactic sky of eROSITA, with the exception of this little tongue here. You have a Gaia and you have a Catwise, and we have to keep in mind that for every of these surveys, the depth is quite different. The type of bands available is quite different. You go from very optical blue object to optical mid-infrared, only mid-infrared. You have that because of the surveys, the wavelengths coverage, you are sensitive to different type of objects. And this has to be kept in mind when you are then going to find the counterparts in these three surveys for the entire sky. You also have to keep in mind that there are area of the sky where you have a huge overdensity of ancillary data. So increasing the area search and having an overdensity of objects increase the probability of getting the wrong association, just a random association. One thing that I also wanted to remind us is that we are limited by the fact that we are always working on catalogs that are prepared usually for other goals than making us happy. They are always going for searching the iRedshift or searching for a cluster, whatever. They are not done for helping AGN population because we are always at 4% of the population and we are not big enough for counting. You know already the concept, so you have many sources to search for, and the other problem that we have is that if you have the wrong catalog for searching the counterpart, you are going to have the wrong association. So this is a real source in XMM from the old paper of Marcella. We know that there is a source in the green area, and using a zeta band catalog, you will be sure that the object in magenta on the top is the right counterpart. In K band, it would be something completely different. And in B, you could choose between 3, 4 objects, and none of them is the right one. And sometimes people forget that this is an issue, and naively, you just go, you take a catalog, and this is my counterpart. And then you find something really weird, and you write a paper about that. It was just the wrong association. So the point is that what you can do instead of choosing one band only or 3 bands independently, you can actually reconstruct the SCDs of all the objects in your image and then learn with a training sample well prepared what is the typical LCD of any X-ray emitter. It can be a cluster, it can be a star, an AGN, a QSO, and so on. Of course, everything comes always with a probability associated, so there is always a margin of error, and also this is often forgotten. People think this is the right counterpart. No, it has a probability of x66% to be the right one. There is always a margin, and people can remember to work with probability. So, as you know, we have developed here Enway a few years back. The code was developed by Johannes, and we were applying it for the first time on the ROSAT, where it was easy to create, or actually we realized by eye that taking a sample of non-AGN, non-X-ray sources with a secure counterpart in the plane W2 versus W1 minus W2, the location of the sources were completely different from the bulk of the all-wise population. Here you have stars, you have elliptical objects, and here you have the quasar that you are interested on. So if you map this plane in, you cut it in grid, in every location of the map, by the ratio of the number of sources that are real versus those that are on the field population, you can kind of assign a probability of an object to be the right counterpart. And we have adopted for ROSAT, but for eROSITA, all the objects are actually going on the bulk of the population. So this method doesn't work, and this combination of bands doesn't work. So again, we went back to training samples, and we have identified many tens of thousands of objects with secure counterpart from Chandra and XMM in legacy survey, in Gaia, in Catwise, used a combination of features that we could find. We made a trial and error, of course. With this combination of features, without looking at the X-ray position of the source, we could give a probability for every source in these catalogs to be the right, to be an X-ray emitter. And then you attach this probability to your input catalog, and you combine it with the probability coming from the separation and distance, and at the end you have the final probability of the source to be the right counterpart. So on the top, what you have is the counterparts from the in the three surveys, color-coded by the probability of being the right one. And as you see, yellow is a 1, and 0 is black. So you have, depending on the area, you have different probabilities. You started to see that in the galactic plane for Gaia, you are not really secure because, as I said, there is overdensity, so chance association is very likely. So in order to quantify this chance association, what you do, you take the X-ray sources, you randomize the position, you redo all the process, and then you quantify, since you should not have any real association in the random position of the sky, you decide at which value you can trust your counterparts. And so for every survey and at different detection likelihood of the eROSITA sources, Andrea was describing before this quantity, you can decide in the catalog whether you want to create your own catalog based on purity or completeness, or just simply maximizing the two curves at the same time. So all this will be in the catalog. You can construct your catalog and have perfect control of the selection function that you need then for making your analysis and maybe compare it with simulations. Classification, this is pretty standardly done by now. We had again another training sample of secure galactic and extragalactic sources with the spectroscopy, and combining all the information coming from legacy survey when available, plus Gaia, legacy survey plus Gaia when available, we managed to have an accuracy of 98% of the in classifying the objects. The yellow here are the sources that are galactic. You see the color code here provided the probability of being extragalactic. So these objects are actually our stars. So 90% of the objects that are nearest one in the legacy survey are actually extragalactic sources. And here you have the distribution of the sources. Again, you have the stars here. This is a kind of plot that we started to use in the IFEDs, but is really helpful for having an idea of the population. Here normally are the quasar, they are redshift high luminosity objects, and here these are the emission that is associated to the most passive objects, and some of them actually are clusters that are misclassified in the point source eROSITA catalog. If you take all the photometry that has a signal to noise higher than 10 out of 750,000 objects, you can create a sample of 550,000 one, assuming, as I said, the signal to noise larger than 3 in GRIZ, W1, and W2. You can also do other selections. I will show some later coming on. For example, you wanted to have the same depth in optical bands, because in this way you are getting the same population everywhere. Instead, if you keep signal to noise larger than 3 only, there are areas where you are extremely shallow, areas where you're very deep, so the population that you are going to handle is completely different, and maybe you are not noticing that. But again, all of this is available, and we are providing scripts for you to use and make your own selection, so you can really make your changes. Hopefully become, instead of a script, this notebook, but we are still working on the idea. Of course, for all our work, photometric redshift is necessary. And these are the photometric redshift accuracy and fraction of outliers from the pencil beam survey. Some of them are not really pencil beam anymore, but they share the same quality in outliers and accuracy, because the number of bands that were available was huge, and the photometry was homogenized in some way. So the photos were actually coming out pretty well. The problem that we are having with eROSITA is that, as I said, we are dominated by objects that are AGN dominated. So the normal photosys fail because most of the catalogs not only have a limited number of bands, but the photometry that is normally provided is model flux. This means that there is an assumption on the model that is fitting the photometry, and these models normally are Cersich or exponential, devoculaire, PSF, but there is no double Cersich able to fit simultaneously a nuclear component and a host component. So these are three examples, a galaxy, an AGN, and a quasar with different models. And you see that depending on the model, you have a different quality of fit. For galaxies and PSF, you can select the right guy. For an AGN, which is in black, there is no a single model flux that is going to work. And this is creating a big issue for us if you are computing photometric redshift in the usual way, namely using only total fluxes from your survey. But if you switch to machine learning, what you can do is actually use the changing flux from aperture to aperture. And you can use the change in color from aperture and aperture. So all these combinations, these are, we are very happy that this quantity is provided from Legacy Survey DR10. You really have a change in the slope as a function of distance from the center of the object. And this is related to the type of object and to the distance, to the size, and thus to the distance of the object. And in this way, we were actually able to keep in mind this point. I have a wrong order of the slides. For IFEDs using SCD fitting with the best photometry in the Hyper Supreme CAM, this was the quality of photosys accuracy and fraction of outliers that we obtained. And then we started to degrade when we went outside the area of the Hyper Supreme CAM, but using circlets, which is the code that we have developed that take into account aperture photometry flux and color changes, you see that we managed to get for the entire ERAS-1 competitive accuracy and even smaller fraction of outliers. And I could not resist last night to match with DAISY. So these are 58,000 not seen AGN in the sample. And you see that we managed to be stable in terms of accuracy and fraction of outliers. A little bit worse, but I didn't make any cut in this plot, with the exception of using only zeta warning equals 0 from DAISY. If I started to look when the photometry is good and so on, the accuracy and the fraction of outliers improve dramatically. But I would say that we are really safe in the photosys that we are providing you for your work. Also because it comes with a PDZ, so you can also use a probability distribution function. So this is, I lost the time, yes, I will be okay. This is the redshift distribution and luminosity redshift distribution, not updated from DAISY. I did not manage to do that part. But what I am interested on now is that we have all the steps, and now we are curious to see which type of AGN we have and how we can compare them with AGN that we are familiar with. Just a reminder, we always show this slide before eROSITA was coming, saying that eROSITA will be crucial for the high luminosity objects and the faint objects and so on. So we were making a lot of propaganda on the expectation that will have come from eROSITA, and this will have been the sources in the IFEDs, so the quasars that are here and the low redshift objects that will be corresponding to this population. And the claim that we always had was that many of these objects, so on one side you have the bright objects that you see because they are strong X-ray emitters, so even if eROSITA is relatively shallow, you will see them. You also see the objects where there is X-ray emission, but the galaxy is hiding it. So you have a lot of low luminosity, low redshift AGN that the other service will not be able to see. And now it is time to see whether we are right. So we start from the eROSITA DR1 catalog with all the sources, and depending on the survey, We do some cut in terms of objects being extragalactic, whether you wanted to have a very low probability of having spurious objects, whether or not you wanted to have all the photometry as deep as possible or only some of the photometry deep. And you can decide the threshold of chance association and so on. So for every of these subgroups, we have different families of AGN. And in particular, I like these two because these are from Gaia and Catwise in the area where you do not have legacy survey DR10. And in particular, this is the area that is in the galactic plane. So for the first time, we are also going to have a very rich sample of AGN in the galactic plane, which is normally is ignored when we do our work. So the gray sources are those coming from the legacy survey with a very good photometry. These are about 320,000. Remember that they were 550,000 if you are happy with the quality of the photometry. If you want to have also the same depth in the photometry, the sample become Gesundheit, become a bit smaller. Which type of objects they are? Again, back to the G minus R, Z minus W1 distribution. We were already saying before, this is color-coded by photometric redshift. The bulk of the high redshift quasar are here, and this is how they are looking. There are also blue objects here, but they are at a kind of a lower redshift. Here you have definitely galaxy dominate, I will say, the entire region here. And here you have the dusty red objects in this region. You also may see that there are dark spots on the top of the nearby object, because you will see later some of the tracks, you also have high redshift in that region, although statistically they are very, very few. So this is again the sample that we have selected, and I apologize for the y-axis in this figure. It should be exactly like this one. One is color-coded as photometric redshift and the other as luminosity. So again, we are saying these are the eROSITA sources that are super bright. And if now we can do is a comparison with the Gaia quasars, selecting those with high probability of being a quasar candidate based on statistic only using Gaia data. Here you have the number of sources that are in the area of the legacy survey, and here is the number of sources that is in overlap. So 2/3 of the eROSITA sources in this group will be in overlap. But you see that, of course, Gaia point-like sources, the extended object that we were seeing in the previous image, are not seen by Gaia. Then you have the all-wise Roberto Assef objects, and again, they do not emit in WISE, so you are going to miss them from that association, that catalog. And finally, you have the Quaia, which is unwise plus unwise and Gaia selected AGN together, having a prior when you go to interpret the redshift from the spectra from Gaia. And again, you see the different type of population that you have. Because these are, so they should be pretty similar, but because you also need to have all-wise, it can be curious that WISE alone extend all over the field, Gaia quasar as well, but then when you put them together, they get much bluer. And the reason is that actually Quaia is unwise and not all-wise, so there are differences in the type of object, plus combining mid-infrared and optical together change a little bit the type of SED of the objects. So here you have the overlap between the surveys with the circles that are proportional to the number of objects. And what you can see is essentially that the 50% of the ERAS-1 sources are unique to that selection, and their distribution is shown in this plot. And again, these are only these objects here on the top in redshift distribution and luminosity. And what we said in the beginning, the low luminosity AGNs are unique to this survey, in particular the ERAS one. As I said, we are going to have also objects in the galactic plane, and there are about 80,000 objects that are in common between ERAS 1, Allwise, and Gaia DR3. So they're really secure objects, and you also have the redshift from Quire. So you can really do a lot of work with the AGN that are in the galactic plane. Physical parameter is the last ingredient, and next week, Johannes is going to have a tutorial on the use of GRASP, the 4th week, okay? And the idea is that we have a lot of codes that claim that they are accounting for the AGN contribution, but each of them have missing, some ingredients is always missing. And one problem that we have in the community is to have a bench test that can be used to quantify the difference between the various codes on the same sample where we know the input stellar mass, and then we can see how good we are in recovering. So what Johannes has done in this paper is taking secure isolated galaxies from cosmos with a very well determined stellar mass with all the photometry that is available, take a sample of very pure quasar with little or nothing, no trace of the galaxy, combine them at the same redshift, and then play with the relative ratio of quasar and galaxy, and then try to run a new code that is called GRASP on this sample and verify whether or not, accounting for all the ingredients that GRASP is including, whether or not we were able to retrieve the stellar mass that was injected. And at the same time, we are also comparing with different codes that claim to have done the same. So I'm very I'm good in terms of time, I will manage. This is just an example for the stellar masses. These are 3 different examples, Tesla 15, I forgot the surname, Nixon 19, yes. And you see all the difference between the input and the output as a function of the luminosity of the object. You have the bias, the error, and the fraction of outliers. And you see that we are all very good when the AGN is not dominating, but then you start to get completely different results when you have a high contribution from the AGN. And mostly the code tends to overestimate the masses with a small error associated with it. GRASP has less overestimate at the cost of having much larger error because it's trying to be accounting for all the possible uncertainties in the measurement. And the same is not only for stellar mass, but we have the same for star formation rate. Other multi-weapon surveys, as I mentioned, now we have the machinery in place, the sky is cutting tiles, we have everything prepared for defining counterparts at other wavelengths. And so we started to have fun in getting the counterparts to racks, and we have we did exactly as we did it for eROSITA using the legacy survey DR10. And what I wanted to show here is what is happening to a source when you use not just RANDEC, but the Bayesian positional match, namely accounting for positional error and the number density of the objects. The probability of an object to have a good counterpart peaks at around 50% because you're not able to distinguish really from field sources or real sources. But in the moment in which you inject the typical SED of a radio emitter and you account for it when you use the Bayesian positional match, then you see that the distribution changed dramatically. You have sources that are clearly not associated and a lot of more sources that are secure associated. So, and these are the interesting radio objects. And if you plot those objects again in G minus R and Z minus, oh, sorry, just wanted to say one thing here, that 20%, even if you're using Bayesian positional match and not just the Ra and Dec, 20% of the sources in RAX change counterpart if you're using a prior typical of radio emitter sources. Here is the distribution of the object in the G minus R and Z minus W1. And as before, you have quasars, you have elliptical, this might now make more sense. You have radio sources in clusters objects and so on. And this is a filler that we submitted to Sloan 5, and we submitted a sample of 150,000 sources. So if you are part of Sloan 5, you have access step by step also to those sources because they are constantly measured. In addition to all this, for the way in which the work is done, you also have a bonus. 1 week ago, William was showing this plot. The probability of an object to be an X-ray emitter or a radio emitter or an infrared emitter is done prior to know whether there is an X-ray source there, a radio source, or an infrared source. It is purely based on comparing the SED of the object with the sources around. So you can create a sample of objects that have a high probability of being an X-ray emitter with a high probability of being extragalactic, and create sample of objects that have been not yet seen from an X-ray survey because it was not deep enough at that moment. And so this is the game that we have done currently on the Euclid data that were just released, but we are ready to do it on the legacy subdirector and Cutwise and Gaia and so on, so that we can really see select objects that have a high probability of being an X-ray emitter and then stacking them and see whether the signal is increasing from this type of sources. And what you see here, these are the best sources in this group. So now, by now, you have learned the distribution. It is kind of weird, this distribution, but I'm actually very happy to show you that this is the location of low redshift Cipher2 objects. So we were wondering whether or not these are real objects or spurious objects. What you see here, this is the track of elliptical and S0 objects. The steps here are 0, 0.2, 0.4, 0.6, 1, 1.3, 1.6. I believe, Katarina, you can confirm. Okay. And you see the type of object that we are not yet seen in X-ray, but we will be able to see in the future. So we have then done the same for the radio sources, and it's nice to see that radio sources from the RAX catalog in the Euclid area, they are they have an overdensity here where, as I said, there are clusters. This is the Euclid deep field south, where indeed there is a cluster in the center of the field. So it all makes sense. So I am at my summary. Number 1 is about the eROSITA catalog. We have 900,000 sources, extra point sources, 750 are in the area of the legacy survey, 550 are good for our work if you are just happy with the signal to noise in the optical photometry larger than 3 in all the bands. If you wanted to have a control also on the depth of the photometry, then they decrease to 320,000. 50% of our AGN are not seen by other AGN selection, and there are additional 80,000 that are in the galactic plane. And all of this is going to be released to you soon so that you can play. We are really, now that I have the chance to have Antonis, Marcella, Andrea here, we are trying to finalize the paper. The other point that I wanted to make is the fact that the future of wide area surveys is great, because we have learned how to prepare the machinery. We have legacy LSST coming on. We have Euclid coming in, so we are going to have 1,000 and 1,000 of square degrees of extragalactic square degrees of sky with very deep photometry, with photometry high quality that can be put together in many bands. Because we are using already eRAS-1, we can increase the training sample that we are using that we have used for eROS1, we can add now the eROS1 sources. So the training sample that we are going to use for eROS3, 5, and so on is going to be richer because we have now new population that maybe were missing. In particular, at the beginning of the work, the obscured AGN were not really enough in the training sample. So I'm kind of confident that in the next versions of our catalogs, there will be new obscure AGN that we didn't realize before were there because the training sample was not educated in identifying them. And finally, what we can do is really start going back to the first point when I was saying that the work on AGN was done generalizing what we have learned from few low luminosity AGN to the entire AGN population. Now combining those studies with the AGN from eROSITA, we are going to be really finally making sense of how, if there is a correlation between galaxy and AGN evolution. Thank you.
How you deal with blends, I guess, when you already have a counterpart for maximum or Chandra Swift, if you're not using Swift and you want to use Swift, you probably do. When you already have counterparts and you can deblend, I guess it's easy. But if we have a source and if we have a probability, from priors, that there's two hosts that could be the host of this source.
Yeah, both right. Yeah. So I can show you an example. I didn't think to put it in, but we have an object, and it is an M star on the top of an AGN at low redshift. They're both right. And this is the problem that we have with our resolution. That object, you have to be careful when you make X-ray flux or luminosity, because that part of that flux is not coming from the AGN, is coming from the M star. This is the problem that we are resolution.
So do we have enough data from the pencil beam surveys to be able to deblend these flux ourselves and say, maybe 70%?
That is a good idea. I didn't attempt yet. It is definitely something that is worth to think about. Thank you for bringing it up, definitely.
Thanks, I really enjoyed this. What fraction of the sources are there for which you don't have any possible identification?
No.
Wait,
In the legacy Savidir 10 area, yes, because the area is deep enough, the data are deep enough in legacy and cutwise to have a counterpart. It can be that going deeper, you will change, but there is I do not have sources that have zero counterpart. They may have a low probability, but there is always something beside. Because at the eROS1 level, the 24 magnitude legacy survey depth and the 21 magnitude of cutwise are deep enough for making an association. If you're asking about eROS5, then the situation changed, because for eROS5 you need the deeper data.
but practically speaking, Mara, you are saying there are 10% sources where you cannot be sure about the counterpart. So among these,
there is a probability that they are something else.
So you're actually telling us we should not take the counter, so we should consider them as without.
No, the probability simply tell is much lower. There is a random sky, there is more or less the same probability. So yes, it could be random, but it can also be this source is not behaving like the training that you gave me. And it can still be the right one. And the PN can only tell you, this is not what I'm used to. It is really something that is worth to investigate. So rather than dropping them, I will try to see whether they are more interesting, actually.
It was slightly more precise in the sense that because of your large PSF, there will always be sources nearby.
Yes.
But in your statistical method, you should also look to estimate that there should be a small fraction of sources for which there likely is no candidate.
So we are accounting for the positional error and the number density of the objects. But what I'm saying is that at the depth of eROS1, if you look at the typical cosmos, say, the X-ray data are much deeper and the optical data are much deeper. And you have counterparts for everything. And you can go back and check at the magnitude of 24, what is the X-ray flux that I'm able to cover. And you see that it is much fainter than what EROS-1 has. So I am telling that at the depth of 24 magnitude in the legacy survey, I am probably getting all my counterparts. It's not the case on the Gaia area because it is too shallow. So it's really depending every time on the ancillary data.
Guys have something really strange that you can't see.
So that is the second time we really go back to those with the low PN. So we found a TD, an Einstein probe object. I don't know if Arne is online, and we assign a spit, literally a spit on the image as counterpart of an X-ray emission. Very low probability, but with Einstein probe and looking with the imaging and study of the transit, it was the right one. So it's really working well.
So I was wondering, do you have plots of probability of AGN as a function of column or inferred column density? Or obscuration, you know, from other data, perhaps not
No,
X-ray data, but
it's come, this is the harvesting. So
right.
we were preparing the catalog for everyone to start to work on.
A related question is in terms of things that are missing in the catalog is the higher redshift. So that beyond redshift 4, it seems like your dark points were all over the place in terms of some of the color.
Correct.
Do you know more about these sources?
Yeah, so we have already found redshift 6 objects. 2 were in the IFEDs, and they were also with PhotoZ computed and SpecZ confirmed. There was a paper of Julian Wolf last year that had 9 new objects, 6 were in EROS-1, and again it was PhotoZ done, so it is working. The majority of the objects at high redshift, not with SCD fitting, but with this measuring the aperture flux, the objects there have the limit that the signal to noise of the image is not good enough or the catalog is not good enough. So before trusting a redshift 6 object, I will look at the quality of the objects. But we, as I said, we made a campaign for 9 objects, and they were, I think they were out of 11, 2 were stars and 9 were objects that redshift higher than 5.5. So it is good.
So one last question from.
That's both Hope and Sylvain, that of course there are other people that are taking approaches different from Mara when you're looking specifically for a very, very small population. I mean, we expect maybe a few dozens of high redshift quasar. We expect a few dozen of isolated neutron star that should not have any counterpart down to maybe 30 and 28 magnitude. I mean, we are expecting a few dozen of new X-ray binaries that are also quite peculiar. So, of course, in these cases, you have to devise a different Bayesian approach, and that's the.
Yeah. So in the group we have we are applying the same procedure for looking for series, for example. Exactly the same procedure, but having a training sample dedicated to CVs, X-ray binary. So every group is training the sample in a different way, and then we compare and see how often we agree or not. Yep.
Okay, so sorry, but we don't have time, so we should move on to the panel. Sorry, we can't keep the discussion during the coffee break, but panel. It's your turn.